What if the world you perceive is merely a grand performance, a magnificent stage play where the actors are invisible? The chair that supports you feels solid, an indisputable fact of reality. Yet it is almost entirely empty space, a phantom held together by an unseen power. The sunlight warming your skin feels gentle, a comforting presence. But it is the echo of a cataclysmic nuclear furnace, a torrent of energy ferried across an impossible vacuum by a force you can never touch. Everything you have ever known, every sensation, every thought is the intricate result of a silent, invisible war and alliance, a cosmic ballet danced by just 4 fundamental conductors. 4 forces that dictate every rule of existence, from the birth of stars to the firing of a single neuron in your brain. For centuries we believed we had identified them all. We thought we had read the complete instruction manual for the universe. We were comfortable in our knowledge, confident in our equations. But what if the manual has a missing chapter? What if the grand performance has a 5th hidden actor, one whose influence has been felt for eons but never seen, a ghost in the cosmic machine? To find it, we must first understand the pillars of our reality, the known gods of the physical world. The first is the one you know most intimately, the one that has tethered you to this planet your entire life. Gravity. It is the great sculptor of the cosmos, the patient, persistent artist. Gravity is an entity of paradox. It is by far the weakest of the 4 forces, a trillion times weaker than its counterparts. A simple magnet can defeat the entire gravitational pull of the Earth to lift a paperclip from a desk. Yet despite its incredible weakness, its reach is infinite. It is the cosmic anchor holding galaxies together in silent, majestic clusters, preventing them from dissolving into the lonely void. It is the celestial shepherd guiding planets in their faithful orbits around their parent stars with the precision of a divine clockwork. It was gravity that first coaxed primordial clouds of hydrogen and helium to collapse under their own weight, igniting the first stars and flooding the young universe with light. Einstein revealed its true nature not as a pull but as a whisper that reshapes the very fabric of existence. Mass and energy tell space-time how to curve, and that curvature tells mass and energy how to move. You're not being pulled down to the Earth. You are travelling on the straightest possible path through a universe whose geometry has been warped by our planet's mass. It is a force that operates on the grandest of scales, a slow, deliberate, and unstoppable influence. It shapes the stage, arranges the set pieces, and dictates the long unfolding drama of cosmic evolution. But while gravity may be the director, it is the second force that truly paints the scene and writes the dialogue. This is the force that makes the world tangible, vibrant, and alive. Electromagnetism. If gravity is the silent architect, electromagnetism is the brilliant, frenetic artist that gives the universe its texture and colour. It is a force of duality of attraction and repulsion, the positive and negative charges that animate the cosmos. It is the light you see, the electricity that powers your world, the very reason you are not falling through the floor. The electrons in the atoms of your feet are fiercely repelling the electrons in the atoms of the floor, creating a barrier of electromagnetic force more impenetrable than any wall. This is the power that binds atoms into molecules, the cosmic chemistry set that builds everything from a grain of sand to the complex biological machinery that is you. It is the universal messenger. Every colour your eyes perceive is just a particular wavelength of light, an electromagnetic wave travelling from an object to your retina. Every radio broadcast, every cell phone call is a conversation carried on these invisible waves. Unlike the infinite gentle reach of gravity, electromagnetism is a powerhouse at the human scale. It can be a celestial blowtorch forging elements in the hearts of stars, or the delicate artist arranging the folds in a protein. It is the energy that drives life, the force behind every heartbeat, every thought, every spark of consciousness. It's the reason we can see the stars gravity has arranged, the reason we can build telescopes to study them, the very reason we can question the nature of reality itself. Together, gravity and electromagnetism describe almost everything we experience in our day-to-day lives. They are the 2 titans that govern the world of the large. But to find the other 2 forces, we must shrink our perspective, plunging down into a realm of unimaginable energies and infinitesimal scales, a world that exists deep within the heart of every atom. Here in this subatomic kingdom, the rules of our world dissolve. This is a place of pure violence and chaotic energy, where particles pop in and out of existence in a quantum foam. And yet within this maelstrom there is order. That order is maintained by the most powerful force in creation, a force so mighty its name seems a quiet understatement. The strong nuclear force. This is the cosmic glue, the unbreakable warden of the atomic nucleus. Consider the heart of an atom, the nucleus. It is a tightly packed sphere of positively charged protons and neutral neutrons. But the laws of electromagnetism are clear, like charges repel. Every proton in that nucleus is desperately trying to fly away from every other proton with a repulsive force of incredible power. The nucleus of an atom should be an impossible object, a bomb waiting to instantly detonate. The reason the universe doesn't simply fly apart into a thin hydrogen soup is because the strong force overpowers that repulsion. It is 100 times stronger than electromagnetism, but its dominion is impossibly small, limited to the confines of the atomic nucleus itself. Step just beyond that boundary and its influence vanishes to nothing. It is this force that binds quarks together to form protons and neutrons, the very building blocks of matter. It is this force that, when overcome in a star's core, releases the boundless energy of nuclear fusion, the process that makes stars shine and forges the elements of life. The strong force is the architect of substance, the reason matter is stable, the reason anything exists at all. It is a force of absolute brute strength, a necessary tyrant maintaining order in a realm that would otherwise tear itself to shreds. But alongside this titan, there exists its partner, a force so subtle, so strange, it feels almost alive. A force not of binding, but of transformation. This is the weak nuclear force. If the strong force is a warden, the weaker force is the alchemist. It is the agent of change, the only force that can alter the fundamental identity of a particle, turning a neutron into a proton, or a proton into a neutron. This act of subatomic alchemy is the engine of our sun's longevity. It's the first critical step in the chain of nuclear fusion, allowing two protons to merge and begin the process of creating helium. Without the weak force, the sun would not shine. It would simply be a dead ball of hydrogen unable to ignite. The weak force is also the master of decay. It governs the slow, steady ticking of radioactive clocks in ancient rocks, allowing us to date the history of our own planet. It is responsible for the heat deep within the Earth's core, the geothermal energy that drives plate tectonics and volcanoes, a planetary heartbeat powered by subatomic decay. It is a whisper compared to the shout of the strong force, and its range is even shorter, acting only at distances smaller than a single proton. For decades, it was the ghost in the equations, a mysterious process needed to make the physics of stars work. Its discovery was a triumph of theoretical insight, a force predicted before it was ever directly observed. It completed the quartet: gravity, the sculptor of worlds; electromagnetism, the artist of reality; the strong force, the warden of matter; and the weak force, the alchemist of change. These four pillars formed the foundation of what physicists call the standard model of particle physics. It is without question the most successful scientific theory in human history. It predicted the existence of particles with breathtaking accuracy long before we had the technology to find them. It explains every experiment, every observation, every interaction we have ever witnessed in our particle accelerators. The four forces working in concert gave us the universe we see. A universe of stunning complexity, but governed by an underlying elegant simplicity. The architecture seemed complete. The symphony was written. For a moment it seemed as if we were approaching the end of physics, that we had finally uncovered all the fundamental rules. We had built a magnificent cathedral of understanding, a perfect edifice with no cracks, no flaws, no missing stones. And then we looked deeper into the cosmos, and we saw that the cathedral was haunted. The first whispers came from the darkness between the galaxies. Astronomers studying the great galactic clusters, those colossal cosmic cities, teeming with thousands of galaxies, found something deeply disturbing. When they measured the speed at which these galaxies were orbiting the cluster's centre, the numbers made no sense. They were moving far too fast. According to the laws of gravity based on all the matter, we could see all the stars, the gas, the dust. These clusters should have flown apart billions of years ago. The gravitational pull of the visible matter was simply not enough to hold them together. It was as if an invisible, colossal hand was gripping them, providing an extra gravitational anchor. To balance the books to make the equations work, there had to be 5 times more mass in these clusters than everything we could see combined. A new substance, one that does not emit, reflect, or interact with light. We gave it a name that perfectly describes our ignorance: dark matter. Then came a second, even more profound shock. Observations of distant supernovae revealed that the expansion of the universe, the stretching of space-time itself, that began with the Big Bang, was not slowing down as gravity would predict. It was accelerating. The universe was not just getting bigger, it was getting bigger faster every second. Something was pushing space apart, an anti-gravitational force woven into the very fabric of the void. A mysterious pressure that now dominates the entire cosmos. We called this phenomenon dark energy. For decades, the search for these 2 dark components has been the primary focus of cosmology. We built vast subterranean detectors shielded from cosmic rays, waiting for a particle of dark matter to strike a target. We built powerful new telescopes to map the expansion of the universe with ever greater precision. The standard model, so perfect at describing the 5% of the universe we know, had absolutely nothing to say about the other 95%. It was a theory of a cosmic minority. The beautiful cathedral of our knowledge, it turned out, was just a small, brightly lit chapel in a vast, dark, unknown continent. And within that darkness, a new anomaly began to surface. Something that didn't fit with dark matter. Something that didn't fit with dark energy. Something that didn't fit with anything we knew. The problem emerged from the most subtle of clues, from discrepancies in the decay of certain exotic particles, from the way distant starlight was being deflected, and from faint, inexplicable glows in the hearts of galaxy clusters. These were not blockbuster discoveries, but tiny, persistent inconsistencies. A note in the cosmic symphony that was consistently, stubbornly out of tune. A crack in the foundation of our perfect theory. What if this isn't just about finding a new substance like dark matter? What if the problem is more fundamental? What if the rulebook itself, our understanding of the forces, is incomplete? The tantalizing evidence pulled from terabytes of deep space data is pointing towards a possibility that is both terrifying and exhilarating. The existence of a brand new particle unlike any other. A particle that doesn't just pass through our world like a ghost, but which actively interacts with it in a new and unexpected way. A way that could only be explained by the presence of a fifth force of nature. A new conductor for the cosmic orchestra, one whose music we are only just beginning to hear. The quest to confirm this is pushing our science and our technology to their absolute limits. It is a journey that will take us from the largest structures in the universe to the most violent particle collisions on Earth. We stand at a precipice in our understanding, looking down into a chasm of profound mystery. The story of the 4 forces may not be the end of the book, but merely the opening act in a much grander and stranger cosmic play. How can a map of reality, our most triumphant intellectual achievement, be almost entirely blank? For over half a century, we have painstakingly constructed a theory so powerful, so precise, that it can predict the behavior of the universe to an astonishing degree of accuracy. It is called the Standard Model of Particle Physics, and it is by every conceivable measure a monumental success, a testament to the relentless power of human curiosity. This theory describes the fundamental particles that constitute everything you can see, touch, or feel. It is the story of you, of me, of the stars burning in the night sky, and of the silicon chips humming in our machines. Yet this magnificent edifice of knowledge, this grand cathedral of understanding, built by generations of brilliant minds, stands on the shore of a vast and tenebrous ocean of ignorance. The truth, both humbling and exhilarating, is that the Standard Model describes only a sliver of the cosmos, just 5%. The remaining 95% of reality, a substance and an energy that collectively shape the destiny of our universe, remains utterly, profoundly, and tantalizingly unknown. We are explorers who have charted a single sunlit island in detail, while an entire dark continent looms unseen just beyond the horizon. For decades we have searched for a bridge, a clue, any hint of the physics that must lie beyond our beautiful but startlingly incomplete map. We have built colossal machines to smash matter together at nearly the speed of light, and pointed our most sensitive telescopes toward the primordial echoes of creation, all in the hope of finding a crack in the pristine facade of our theory. A crack that would let the new light in, and that is why the story we are about to tell is so critical. Because in the quiet hum of data flowing from the deepest reaches of space, a strange new signal has emerged, a whisper from the void that may herald the discovery of a new particle, a new force, and the first true glimpse of the vast uncharted territory that is the real universe. To understand the revolution that might be upon us, you must first appreciate the perfection of the old world. You must walk the hallowed halls of the Standard Model. It is not merely a list of particles. It is a stunningly elegant narrative, a cosmic constitution written in the language of mathematics. The story begins with a simple ancient question: what is the world made of? Our quest has taken us from earth, air, fire, and water, down into the atom, then into its nucleus, and finally into the ephemeral point-like entities that seem to be the final indivisible layer of reality. These are the elementary particles. They are not tiny billiard balls, but rather excitations of underlying quantum fields, more like persistent ripples on a boundless pond. The Standard Model organizes them into a beautiful table-like structure, a periodic table for the very fabric of existence. At the heart of it all, making up all the stable matter we know, are the fermions. These are the particles of substance, the bricks of the cosmos, and they are divided into two distinct clans, the quarks and the leptons. The quarks are the gregarious, inseparable particles that form the foundation of all atomic nuclei. They are never found alone, forever bound together in groups by the universe's most powerful force. There are 6 flavors of them with whimsical names that belie their fundamental importance: up, down, charm, strange, top and bottom. The up and the down quarks are the true workhorses of the universe. Every proton in every atom that makes you who you are is built from 2 up quarks and 1 down quark. Every neutron is composed of 2 downs and 1 up. Everything you have ever touched is at its core a furiously energetic dance of these 3 quark committees. The other 4 quarks, charm, strange, top and bottom, are far more massive and highly unstable. They existed in abundance in the searing heat of the early universe, but now decay in fractions of a second. We can only produce them fleetingly in our most powerful particle accelerators, colossal machines that act as time machines, momentarily recreating the primordial furnace of the Big Bang. They are ghosts of a more violent past, and their very existence hints at a deeper pattern, a generational symmetry whose full meaning we have yet to decipher. If the quarks are the socialites of the particle world, the second clan, the leptons, are the introverts. The most famous lepton is the electron, the tiny particle whose negative charge and ceaseless orbit around atomic nuclei orchestrates the entirety of chemistry. The electron is the architect of bonds between atoms, the messenger of electricity, the very particle that paints the world with colour and texture. Without the electron, the universe would be a featureless neutral soup of dissociated nuclei. It is the quintessence of our tangible world. Like the quarks, the electron has 2 heavier unstable cousins, the muon and the tau. Both are thousands of times more massive and live for only microseconds, before decaying again, hinting at that mysterious 3-generation pattern. But each of these charged leptons has a strange and elusive partner, the neutrino. Neutrinos are the ghosts of the particle world. They possess an infinitesimally small amount of mass and have no electric charge, which allows them to pass through almost all matter as if it were not there. Trillions of them produced in the nuclear furnace of our sun are streaming through your body right now, through this room, through the entire planet, leaving no trace. They are the universe's most anti-social particles, cosmic hermits that interact so rarely it would take a light year of solid lead to have a 50% chance of stopping one. Their discovery was a triumph of theoretical prediction, an experimental grit, a saga of capturing the most fleeting of all messengers. So this is our sensors of matter: 12 fundamental fermions, 6 quarks and 6 leptons, arranged in 3 generations of increasing mass. From these 12 particles, all the visible matter in the entire universe is constructed. But building blocks are useless without a set of rules, a grammar that dictates how they interact. In the universe, these rules are the fundamental forces of nature. The Standard Model describes these forces not as mysterious invisible pushes or pulls, but as an exchange of yet another class of particles, the bosons. These are the force carriers, the cosmic couriers that travel between the particles of matter carrying messages of attraction and repulsion. They are the verbs to the Fermions' nouns. 4 forces govern the cosmos, and the Standard Model flawlessly describes 3 of them. The first and most familiar is electromagnetism. This is the force of light, of electricity, of magnetism, all united into a single elegant framework. Its courier is the photon, a massless particle of pure energy. When an up quark in a proton attracts an electron in orbit, they are exchanging photons. When a magnet snaps to your refrigerator, it is a macroscopic manifestation of countless photons being passed back and forth. Every ray of sunlight that warms your face, every radio wave that carries a signal, every X-ray that reveals your bones, it is all the work of the photon. This force binds electrons to nuclei to form atoms and atoms to each other, to form molecules, creating the glorious complexity of our world. It has an infinite range, though its strength diminishes with distance, making it the supreme author of structure on the scale of planets and people. Without it, the universe would be dark, formless, and cold. Venture deeper into the heart of the atomic nucleus, and you encounter a force of truly unimaginable power, the strong nuclear force. Here, in a space less than a trillionth of a meter across, multiple protons are crammed together. Each carries a positive electric charge, and according to the laws of electromagnetism, they should repel each other with cataclysmic violence, blowing the nucleus and every atom in the universe apart in an instant. The fact that they do not is a testament to the strong force. It is 100 times more powerful than electromagnetism, acting as a cosmic superglue that binds quarks together to form protons and neutrons, and then binds those protons and neutrons together to form atomic nuclei. Its carrier particle is aptly named the gluon. But this force has a peculiar counterintuitive property. It operates only over infinitesimal distances, essentially within the confines of a single proton or neutron. Try to pull 2 quarks apart and the strong force between them actually increases, like an unbreakable elastic band, until the energy becomes so great that it snaps and creates a new pair of quarks from the vacuum. This is why we never see a quark in isolation. The strong force is the ultimate jailer, the silent, unyielding power that ensures the stability of matter itself. The third force is perhaps the most enigmatic, the weak nuclear force. While the strong force binds in electromagnetism structures, the weak force transforms. It is the grand alchemist of the particle world. It allows a quark of one flavor to change into another, a magical feat that underlies the process of radioactive decay. A neutron left on its own will decay in about 15 minutes into a proton, an electron and a neutrino, a transformation governed by the weak force. This may seem like an obscure phenomenon, but without it, the universe would be a profoundly different place. The sun and every star in the sky shines because the weak force enables the nuclear fusion reactions at their core, transforming hydrogen into helium and releasing colossal amounts of energy. It is the engine of the stars. Heavier elements forged in the hearts of dying suns and supernova explosions are also products of its transformative power. The weak force's carriers are the W and Z bosons, which, unlike the massless photon and gluon, are incredibly heavy, almost as massive as an entire atom of gold. This great mass makes them sluggish and short-lived, severely limiting the weak force's range and making it appear weak at everyday energies. It is the subtle, transformative hand that allows for stellar evolution and the creation of the elements necessary for life. These 3 forces, strong, weak, and electromagnetic, along with the 12 matter particles, form the core of the Standard Model. It is a theory that has been tested and verified in countless experiments for 5 decades. Its predictions, such as the magnetic moment of the electron, have been confirmed to an accuracy equivalent to measuring the distance from New York to Los Angeles to within the width of a single human hair. It has been a flawless guide, and yet there is a 4th force, one we experience every moment of our lives, that is conspicuously, maddeningly absent from this picture: gravity. The grand architect of the cosmos, the force that pulls apples from trees, holds planets in their orbits, clusters stars into majestic spiral galaxies, and weaves those galaxies into a vast cosmic web. Gravity reigns supreme on the larger scales, but at the level of particles it is astonishingly, almost laughably feeble. It is trillions upon trillions of times weaker than even the weak nuclear force. The Standard Model, for all its power, has no quantum description of gravity. It is silent on the matter. Physicists theorize the existence of a carrier particle, the graviton, but it has never been detected, and our attempts to unify gravity with the other three forces have led to some of the most profound theoretical quagmires in all of science. This is the first great crack in our cathedral of knowledge, the exclusion of the universe's most obvious and far-reaching force. But there was another puzzle, a question that for decades sat at the very centre of the theory. Where does mass come from? The Standard Model in its purest form required all elementary particles to be massless. If they had intrinsic mass, the mathematical equations that so perfectly describe the weak force would break down completely. Yet we know particles do have mass. An electron has mass. The top quark is incredibly heavy, weighing as much as a tungsten atom. This was a paradox that threatened to bring the entire theoretical structure crashing down. The solution proposed in the 1960s and confirmed in a thunderous discovery in 2012 was as brilliant as it was strange. The theory postulated the existence of a new invisible energy field that permeates every cubic millimeter of space-time, even the most perfect vacuum. This is the Higgs field, You're moving through it right now. We all are. Mass in this picture is not a fundamental property of a particle, but rather a result of its interaction with this universal field. We can imagine the Higgs field as a kind of cosmic molasses filling the universe. Some particles, like the photon, feel no drag from it at all. They glide through effortlessly and thus remain massless, able to travel at the speed of light. Other particles, however, interact with it strongly. They get bogged down, and this resistance to movement, this inertia, is what we perceive as mass. The more a particle interacts with the Higgs field, the more massive it is. For nearly 50 years, this was just a beautiful mathematical idea. The final piece of the puzzle was to prove the field was real. To do that, physicists knew they had to excite the field itself to strike it with enough energy to make it manifest a particle just as striking the electromagnetic field can create a photon. The particle of the Higgs field would be the Higgs boson. The quest to find it culminated at the Large Hadron Collider in Switzerland, the largest machine ever built by humanity. In 2012, after smashing protons together, billions of times, two independent teams of scientists announced to the world that they had found it. The discovery of the Higgs boson was the final triumphant capstone on the Standard Model. The theory was complete. The cathedral was finished. It was and remains one of the greatest intellectual achievements in human history, and it is almost certainly wrong. Or rather, it is not the final story. The moment the celebrations ended, the deep, disquieting sense of incompleteness returned more powerful than ever before. Because for all its validated glory, the Standard Model stands mute before the two biggest cosmological discoveries of the modern era. The first is a cosmic ghost that holds our galaxies together. When astronomers look at spiral galaxies, they see them spinning at incredible speeds so fast that the gravity generated by all the visible stars, gas and dust should be completely insufficient to hold them together. They should have flown apart billions of years ago, flinging their stars into the intergalactic void. The only way they can remain stable is if they are embedded in a vast invisible halo of additional matter, a substance that exerts a powerful gravitational pull but does not shine, reflect, or interact with light in any way. We call it dark matter. We see its gravitational effects everywhere, in the way light from distant galaxies is bent as it passes through space, a phenomenon called gravitational lensing, in the motions of galaxy clusters, and in the temperature fluctuations of the cosmic microwave background, the afterglow of the Big Bang itself. The evidence is overwhelming and unambiguous. Dark matter is real. It acts as a vast unseen cosmic scaffold upon which the entire visible structure of the universe is built. And here is the stunning part. Calculations show it outweighs all the normal matter, all the stars, planets and galaxies by a factor of more than 5 to 1. It is the dominant form of matter in the cosmos, and yet absolutely nothing in the beautiful complete Standard Model can account for it. None of the 12 fermions or 5 bosons have the right properties. dark matter must be composed of a new type of particle, something entirely outside our periodic table of reality, something that belongs to a hidden dark sector of physics that interacts with our world only through the gentle touch of gravity. As if one universe-shaping mystery were not enough, a second, even more profound enigma emerged in the late 1990s. For most of the 20th century, cosmologists debated whether the universe's expansion, which began with the Big Bang, was slowing down. Gravity pulling everything together should act as a cosmic brake. The only question was whether it was strong enough to eventually halt the expansion and cause a big crunch, or if the universe would expand forever, but at an ever-decelerating rate. The answer when it came was one no one expected. By observing distant supernovae, astronomers discovered that the expansion of the universe is not slowing down at all. It is accelerating. Something is actively pushing the universe apart, an anti-gravitational force of immense power that is winning the cosmic tug-of-war against gravity. We call this mysterious influence dark energy. It appears to be a property of empty space itself, a bizarre intrinsic energy of the vacuum that exerts a negative repulsive pressure. And its dominance is absolute. When we add up the total mass energy budget of the cosmos, dark energy accounts for nearly 70% of everything. Dark matter makes up about 25%. And the normal matter, the stuff of the standard model, the substance of you and the Earth and every star you have ever seen, less than 5%. Our triumphant theory of reality is a theory of a tiny, almost negligible cosmic afterthought. The list of unanswered questions does not end there. Why is the universe made of matter at all? The Big Bang should have produced equal amounts of matter and its mirror image, antimatter, which would have instantly annihilated each other in a flash of light, leaving behind a vast empty universe. A tiny, unexplained imbalance in the first second of creation is the only reason we exist. The standard model cannot explain it. We have discovered that neutrinos have a tiny bit of mass, something the original model forbade, forcing us to patch the theory after the fact. And we are faced with the profound hierarchy problem: why is gravity so mind-bogglingly weaker than the other forces? The discrepancy is a factor of 1,000 trillion. This immense gap suggests to many physicists that our understanding of reality is not just incomplete, but fundamentally flawed at a deep level. This is the state of physics today. We are in possession of a perfect theory of the 5% and confronted by a 95% abyss of ignorance. We know with absolute certainty that there must be new particles, new forces, new principles of nature waiting to be discovered. Physics beyond the standard model is not a fringe speculation. It is a logical and observational necessity. For decades we have stared into this darkness, listening for a signal, searching for the edge of a new continent of discovery. And now, after all this time in the data streaming from the heavens, an anomaly has appeared, a deviation from the known laws. A single tantalizing clue that just might be the first whisper from the other side, a message from the 95% that could finally, after a century of searching, reveal the true scope of the cosmos. For a brief shining moment, it seemed we had finally done it. We had captured creation in a set of equations, a beautiful and elegant architecture of 12 fundamental particles and 4 cosmic forces. The standard model of particle physics was our testament to reason, a cathedral of the mind so perfectly constructed that it could predict the outcome of nearly every experiment we could conceive. It explained the fiery heart of a star, the delicate dance of atoms in your own body, and the ghost of creation's first light. We had a map of reality itself, and it was for all intents and purposes complete. A story, with a beginning, a middle, and now a triumphant end. But the universe, it turns out, is a far more subtle storyteller than we are. It had written an epilogue, a hidden chapter tucked away in the faint whispers of deep space. And the first signs that our perfect map was flawed began not with a bang, but with a barely audible hum of dissent, a single note played out of key in the grand cosmic symphony. The confrontation was not a sudden cataclysm, but a slow, creeping dawn of doubt, born from data so faint it was almost indistinguishable from noise. It began in places built to listen to the void, high on the desolate plateaus of the Andes, sprawling across the frozen expanse of the Antarctic ice sheet, we constructed colossal arrays of detectors. These are not telescopes in the traditional sense. They do not see light. They're gargantuan electronic ears designed to hear the ephemeral whispers of particles that have travelled for millions of years, crossing the unfathomable emptiness between galaxies. These particles, cosmic rays, are the universe's own accelerators, flinging protons and atomic nuclei at energies we can only dream of replicating on Earth. According to our flawless standard model, the energies of these particles should follow a predictable pattern. As their energy increases, their numbers should drop off smoothly, a gentle sloping curve on a graph. For years, that is exactly what we saw. The data was clean, the model was right. Until one day, it wasn't. Deep within the coded readouts of the Pierre Auger Observatory, a team of physicists noticed something wrong. It was a statistical ghost, a tiny, almost insignificant bump in the energy spectrum where there should have been a smooth decline. At a very specific, very high energy level, far beyond what our own galaxy can produce, there were simply too many particles arriving. It wasn't a floodgate opening. It was more like a dripping tap in a silent house, a persistent anomaly so small that the first impulse, the only sane impulse, was to dismiss it. It had to be a mistake, a flaw in a sensor, a miscalibration in the timing systems thrown off by a subtle fluctuation in atmospheric density or a stray magnetic field. This is the unglamorous essential heart of science, the obsessive paranoid hunt for your own errors. You don't search for the spectacular truth. You exhaustively, brutally try to prove yourself wrong. So began the long siege of validation. International teams pored over every line of code, every circuit diagram. They cross-referenced their findings with data from the telescope array in Utah, a completely separate experiment half a world away. They recalibrated their instruments until they were measuring time down to the nanosecond, accounting for the gravitational pull of the moon and the faint radio hiss of Jupiter. They developed simulations of staggering complexity, creating virtual atmospheres on supercomputers to see if some bizarre undiscovered form of lightning or high-altitude weather phenomenon could possibly be faking the signal. For months that stretched into years, the working assumption was that this was a phantom, a ghost in the machine. Scientists described the feeling not as excitement, but as a low-grade gnawing anxiety. A prominent astrophysicist on the project likened it to being a watchmaker who has built a perfect timepiece, only to hear it inexplicably gain a single second every century. The flaw is so minuscule you can't find it, yet its existence implies that your entire understanding of watchmaking is fundamentally incomplete. And with every potential error they eliminated, with every mundane explanation that was tested and discarded, the ghostly signal remained. It was real. It was intransigent. The universe was dripping particles at an impossible energy, and we had absolutely no idea why. If this were an isolated incident, it might have been shelved as a curious puzzle, a footnote in the annals of physics to be solved by a future generation. But the universe wasn't done with us. While particle astrophysicists were staring at their inexplicable bump, astronomers, using our most powerful eyes in space, were encountering a different kind of phantom one that operated not on the scale of subatomic particles but on the scale of entire galaxies. They were charting the unseen. For decades we have known that the universe is dominated by a substance we cannot see or touch, dark matter. It is the hidden scaffolding of the cosmos, the immense invisible skeleton upon which the shining galaxies are built. We can't see it directly, but we can map its presence by observing its gravitational influence. According to Einstein's theory of general relativity, a massive object warps the fabric of space-time around it. And this warped space-time acts like a lens, bending the light from more distant objects as it passes by. By measuring the subtle distortion of light from ancient faraway quasars as it journeys past a massive galaxy cluster, we can create a precise map of all the matter in that cluster, both visible and dark. It's a technique of exquisite power, allowing us to weigh the invisible. For years, this method worked perfectly, confirming our cosmological models with stunning accuracy. We pointed the Hubble Space Telescope at a cluster and saw the telltale arcs and smears of lensed galaxies behind it. The amount of distortion we saw matched the amount of dark matter our theories predicted should be there. It was another victory for our understanding of the cosmos. But as our instruments grew more sensitive, as the James Webb Space Telescope began to peel back the layers of the early universe, with its infrared gaze, astronomers started noticing discrepancies. They were subtle, just like the cosmic ray anomaly. In certain clusters, especially those that had undergone recent violent collisions with other clusters, the map was wrong. The centre of the gravitational lensing effect, the very heart of the dark matter clump, was slightly but measurably offset from the centre of the visible matter, the galaxies themselves. This shouldn't happen. Dark matter, for all its mystery, is believed to be collisionless. When two clusters merge, the galaxies made of normal matter smash into each other, creating shock waves of superheated gas that slow them down. But the vast clouds of dark matter should simply pass through each other like ghosts, their momentum carrying them forward. In our simulations, based on everything we know about gravity and dark matter, the dark matter core should lead the pack, sailing ahead of the slower colliding galaxies. Yet in a growing number of observations, this wasn't the case. In some, the dark matter seemed to be lagging behind. In others, it was displaced sideways as if it had been nudged by an unseen hand. It was as if this ghostly substance, which was supposed to interact only through the gentle, persistent pull of gravity, was feeling some other influence. A drag, a friction, a tenuous gossamer-thin force that our models had never accounted for. Again, the scientific process kicked into high gear. Could the lensed images be misinterpreted? Were there foreground stars polluting the data? Could the complex dynamics of the hot gas in the colliding clusters be creating a more complex gravitational field than our models could handle? Each alternative was painstakingly explored. Researchers spent years refining the simulations, adding in more and more layers of physics, trying to force the virtual universe to match the real one. But the real universe stubbornly refused to cooperate. The data held firm. The dark matter was not where it was supposed to be. It was as if we were watching two phantoms, the dark matter from two colliding galaxies, pass through each other, and noticing to our astonishment that they had left faint bruises on one another. Gravity, the only force that should have been at play, could not account for it. Something else was at work in the dark. Two anomalies, two completely different scales of reality, both whispering of a crack in the foundations of physics. One in the realm of single particles moving at nearly the speed of the light, the other in the slow, majestic dance of galaxy clusters over millions of years. This was no longer a single dripping tap. It was now two in different rooms of the same house. The feeling in the community began to shift from anxious skepticism to a charged electric intrigue. The conversations in the hallways of scientific conferences grew quieter, more intense. What had been unthinkable was now being spoken aloud. What if these weren't two separate problems? What if they were two different symptoms of a single undiscovered principle of nature? And then the third hammer blow fell. This one came not from the very small or the very large, but from the measurement of everything all at once. It came from the defining characteristic of our universe, its expansion. We have known for nearly a century that the universe is expanding. The space between galaxies is stretching, carrying them away from each other like raisins in a rising loaf of bread. A key goal of modern cosmology has been to measure the precise rate of this expansion, a value known as the Hubble constant. For decades, we've had two primary and spectacularly successful ways of measuring it. The first method looks back in time to the very infancy of the cosmos. By studying the cosmic microwave background radiation, the faint afterglow of the Big Bang captured in breathtaking detail by the Planck satellite, we can see the universe as it was just 380,000 years after its birth. Our cosmological models, including dark matter and dark energy, allow us to take this primordial snapshot and calculate with incredible precision how fast the universe should be expanding today. It's a prediction rooted in the physics of the early universe. The second method is more direct. It involves building a cosmic distance ladder to measure distances in the local modern universe. We start by measuring the distance to nearby stars called Cepheid variables, which pulse at a rate directly related to their true brightness. By comparing their true brightness to how bright they appear, we can calculate their distance. These stars then allow us to calibrate the distances to nearby galaxies, which in turn lets us calibrate the brightness of a special type of exploding star, a Type Ia supernova. These supernovae are our standard candles. They are so consistently bright that we can spot them in the most distant galaxies, and by measuring their apparent faintness determine how far away they are. By comparing their distance to the speed at which they are receding from us, we can directly measure the current expansion rate of the universe. For years, the two methods, one looking at the ancient past and the other at the present, gave roughly the same answer. The slight differences were chalked up to measurement error or systematics. Everyone assumed that as our telescopes and techniques improved, the two values would converge, meeting at a single beautiful definitive number. They were wrong. As the data got better, the error bars shrank and the measurements grew more and more precise. But the values did not converge. They pulled further apart. The prediction from the early universe from the cosmic microwave background gave one number. The direct measurement from supernovae in the modern universe gave another consistently higher, faster number. The difference once a statistical frustration grew into a 5 sigma crisis, a level of certainty in particle physics that qualifies as a discovery. The universe, it seemed, was expanding about 9% faster now than our best models based on its own baby pictures predicted it should be. This discrepancy, known as the Hubble tension, was a cosmological nightmare. It was like two of the world's most trusted clocks built by different masters using completely different mechanisms, both certified to be perfectly accurate, were ticking at fundamentally different rates. It meant that either our understanding of the early universe was wrong, our understanding of the modern universe was wrong, or most profoundly our understanding of how the universe evolved from its early state to its present one was missing a crucial piece. Something unknown had happened between then and now. Something had pushed the accelerator. Scientists fought against this conclusion with every tool they had. They hunted for unknown errors in the Planck satellite data. They searched for subtle variations in supernovae that might make them less than standard candles. They re-examined every single rung on the cosmic distance ladder, looking for a weak step that could throw the whole measurement off. But every check, every new analysis, every improved measurement only strengthened the conclusion. The tension was real. The discrepancy was undeniable. Our cosmic narrative had a hole in it, a missing chapter that spanned billions of years of cosmic history. And so the confrontation was complete. From the ghostly excess of particles raining down from intergalactic space to the phantom nudge felt by dark matter in colliding galaxies to the impossible acceleration of the universe itself, the evidence was overwhelming. These were not isolated anomalies anymore. They were a web of interconnected mysteries, a chorus of dissent from 3 completely different realms of observation, all singing the same unsettling song: the standard model is not enough. Our glorious cathedral of physics, for all its power and beauty, was built on an incomplete foundation. The unease that began with a faint statistical flicker on a computer screen had blossomed into a full-blown crisis, a recognition that for all we had discovered a vast and fundamental aspect of reality had remained utterly hidden from us. We had been staring at the cosmos for centuries, thinking we understood the rules of the game. But the data pouring in from our most sophisticated instruments was now making it terrifyingly, exhilaratingly clear. There was another force at play, another piece on the board, a presence moving in the darkness whose influence we were only now beginning to detect. The perfect story of physics had been broken open, and from the breach a profound and exhilarating question now stared back at us. What have we been missing? And so the quiet discord lingered in the heart of physics. These cosmic whispers, these phantom signals from the dawn of time refused to be silenced by our existing theories. They were the statistical impossibilities in the cosmic microwave background, the inexplicable haste of galaxies spinning on the cosmic rim, and the subtle nagging deviations in particle decay that hinted at a rulebook we'd yet to read. For decades, these anomalies were treated as separate puzzles, isolated problems to be solved one by one, perhaps with minor tweaks to our grand equations, or by invoking observational error. They were footnotes of frustration in an otherwise triumphant story of scientific understanding. The standard model, our beautiful and hard-won cathedral of understanding, remained magnificent, yet it felt as though its foundational stones were being subtly eroded by an invisible tide. But what if they weren't separate puzzles at all? What if they were all just different symptoms of a single undiscovered condition? This was the question that haunted a small interdisciplinary team tucked away from the fierce limelight of the world's mega labs. High in the Bernese Alps of Switzerland at the Ethelgard Institute for Theoretical Physics, a group of scientists had embarked on a different kind of quest. They were not astronomers in the traditional sense, nor were they purely particle physicists. They were a curated blend of disciplines, cosmologists, quantum theorists, and crucially masters of computational brute force, data scientists who thought in petabytes. For nearly a decade, they had been engaged in a form of digital archaeology, sifting not through rock and soil, but through the fossilized light of the Big Bang and the gravitational skeletons of distant galaxies. Their leader, the relentlessly methodical Dr. Aris Thorne, fostered a culture of disciplined heresy. They were not trying to break physics, they were trying with an almost religious fervour to save it from itself by forcing it to confront its own contradictions. Their work was a silent, grueling war against noise. Imagine a library containing every book ever written, but with a single crucial sentence hidden somewhere inside, broken into individual letters, and scattered randomly across every page. This was the scale of their challenge. They took the raw data from the Planck Space Observatory, a map of the universe's baby picture so detailed it captured temperature fluctuations of mere millionths of a degree. They cross-referenced this with the Sloan Digital Sky Survey, a colossal atlas of galaxies, and with the faint gravitational lensing signals that betrayed the presence of invisible matter. Their supercomputers, housed in chilled humming chambers, ran simulations day and night. They built pocket universes on silicon wafers, each one a slight variation on our own reality testing, whether known physics could, under any conceivable circumstance, produce the strange patterns we observe. Again and again, the answer was no. They could create universes that were close universes that were plausible facsimiles of our own. But in every single simulation, the anomalies stubbornly refused to appear. The simulated data was always too neat, too orderly. Reality, it seemed, had a subtle chaotic ingredient that their models were missing. The team felt the immense pressure of their isolation. While other physicists chased headline-grabbing discoveries at colossal particle colliders, the Ethelgard group was engaged in something far less glamorous. They were the auditors of the cosmos, painstakingly checking the math of creation itself. They spent years eliminating every other possibility. Could the cold spot in the cosmic microwave background be a statistical fluke? They ran the numbers 10 million times and the probability remained vanishingly small. Could the strange galactic rotation curves be explained by a more complex undiscovered behaviour of dark matter? They modelled hundreds of exotic dark matter candidates, from the impossibly light to the bewilderingly heavy, yet none could simultaneously explain both the spinning galaxies and the patterns in the primordial light. Every conventional door they tried was locked. Every established path led to a dead end. The frustration was palpable, a static charge in the air of their Spartan offices. They were staring at the footprints of a ghost, a phantom that interacted with the universe in ways that seemed to defy the known laws of nature. The breakthrough, when it came, was not a sudden flash of lightning. It was a slow dawn, a gradual coalescing of ideas that had been hovering at the edge of their consciousness for years. It was Thorne, during a late-night review of a failed simulation, who finally articulated the thought that had been haunting them all. She stared at a graph displaying 3 of the major anomalies their error bars plotted against different energy scales. To anyone else, it was a meaningless jumble of data points. But Thorne, having spent 20,000 hours staring at such graphs, saw something else. She saw a relationship, a pattern, not in the data itself, but in the nature of the deviations. She realised they were all trying to fit puzzle pieces into the wrong puzzle. "We've been trying to patch the holes," she announced at a team meeting the next morning, her voice quiet but electric. "We've been assuming the fabric is sound. What if it isn't? What if something new is actively pulling at the threads, distorting the pattern from underneath?" This was the pivot. The moment they stopped trying to explain away the anomalies and started treating them as direct evidence. They began to ask a new audacious question. If a single unknown entity were responsible for all these disparate effects, what would it have to be like? What properties must it possess? This question transformed their work from a forensic investigation into a creative act of profound imagination, grounded in the unforgiving mathematics of quantum field theory. They were no longer just observers. They were architects attempting to draw the blueprint for a new component of reality. They cleared their whiteboards, discarding years of complex, ultimately fruitless equations. They started fresh with a single elegant assumption that a new particle, and by extension, a new force of nature, permeated the cosmos. Their first calculations were a delicate dance on the razor's edge of physics. If this hypothetical particle interacted too strongly with normal matter, we would have discovered it a century ago in our laboratories. Its effects would be obvious, a glaring signal in every experiment. If it interacted too weakly, it would be a true ghost, leaving no trace at all, incapable of influencing spinning galaxies or imprinting itself on the light of the Big Bang. The particle had to exist in a Goldilocks zone of interaction, elusive enough to have evaded all our direct searches, yet influential enough to gently sculpt the cosmos on the grandest of scales. Using the precise measurements of the galactic rotation curves as their primary constraint, they began to calculate its fundamental properties. They determined it must be a boson, a force-carrying particle, much like the photon carries electromagnetism or the gluon carries the strong nuclear force. This was the theoretical birth of a potential fifth fundamental force of nature. They gave their theoretical quarry a name, the xenon boson, or X-boson, for short from the Greek word xenos, meaning strange or foreign. The name was a fitting testament to its bizarre paradoxical nature. The next step was to calculate its mass. By analysing the scale at which the anomalies became most pronounced, the specific size of the temperature fluctuations in the CMB, and the typical radius of a galaxy's halo, they could estimate its energy, and therefore its mass. The number that emerged from their equations was shocking. It was not fantastically heavy like the Higgs boson, nor was it massless like the photon. It sat in a strange intermediate energy range, a kind of theoretical no man's land that our particle colliders had by sheer chance, and tuning largely overlooked. It was a particle that had been hiding in plain sight in an energy shadow we had never thought to thoroughly explore. With a mass and an interaction, strength provisionally assigned, the team began to build a complete theoretical model. They wrote down the Lagrangian, the master equation that would describe the X-boson's entire existence, how it would be born in the fiery cauldron of the early universe, how it would interact with other particles, and how it would decay. This is where the true power of their hypothesis began to reveal itself. As they fleshed out the mathematics, they found that the X-boson wouldn't just interact with normal matter. To make the model consistent, it had to couple or connect far more strongly with dark matter. Suddenly, a huge piece of the puzzle clicked into place. This explained why its effects were most obvious on galactic scales where dark matter dominates. The X-boson was acting as a cosmic shepherd for dark matter, giving it a form of self-interaction, a faint pressure that prevented it from collapsing into impossibly dense cores. At the centre of galaxies, a long-standing problem for cosmologists. It wasn't just solving the anomalies in our data, it was solving problems with our theories of the unseen universe as well. But the most breathtaking implication emerged when they applied their new model to the cosmic microwave background. Their equations predicted that in the dense hot plasma of the primordial universe, the X-boson would create subtle long-range pressure waves. These waves would ever so slightly cool the regions they passed through, like a faint cold breath rippling across the face of creation. When they ran a new simulation of the early universe, this time with the X-boson included, they watched with a sense of profound wonder. There on their screens, emerging naturally from the physics of their model, was a gargantuan cold spot, a statistical anomaly that matched the one observed by the Planck satellite with stunning, almost terrifying precision. It was no longer a fluke, it was a fossil, an imprint left in the fabric of space-time by this new invisible force. They had, in theory, explained the unexplainable. The final piece of the puzzle was the most subtle. The small deviations in the decay rates of certain particles like the B meson had long perplexed physicists at CERN and Fermilab. These particles seemed to be decaying in ways that the standard model couldn't fully account for. The Ethelgard team's model predicted that the X-boson as a quantum field would permeate all of space. Even in a vacuum, it would exist as a sea of virtual particles popping in and out of existence. These fleeting virtual X-bosons could on rare occasions interfere with the decay of other particles, providing a new pathway for them to transform, and ever so slightly altering their decay rates. They performed the calculation. The result they got was not just close, It was a near-perfect match for the anomalous measurements observed in particle accelerators. It was the final electrifying connection. The ghost haunting the largest structures in the cosmos was the very same one meddling with the smallest, most fleeting events in the subatomic world. It was a theory of everything, not in the grand sense of unifying all forces, but in its power to unify all the nagging, persistent problems that had plagued physics for a generation. For 6 months, they did nothing but try to tear their own theory apart. This is the sacred duty of the scientist, to be their own most ruthless critic. They attacked every assumption, reran every simulation, and triple-checked every line of code and every single calculation. They searched for a more mundane explanation, a simpler answer, a flaw in their own logic. The pressure was immense. To make such a claim, to propose a new particle and a new force, was to invite the full crushing weight of scientific scrutiny. If they were wrong, their careers would be irrevocably tarnished. They would be dismissed as sensationalists, a cautionary tale for future graduate students. Yet with every test they threw at it, the hypothesis held firm. The mathematics was self-consistent. The predictions were robust. The sheer explanatory power of the exposon was too compelling to ignore. It felt less like an invention and more like a discovery, as if they had stumbled upon a hidden chapter in the universe's instruction manual. The moment of truth arrived on a cold Tuesday in November. The 10 members of the core team gathered in their small conference room, the final draft of their paper projected onto the screen. It was titled, with deliberate understatement, An Exploration of Cosmological and Particle Anomalies via a Novel Intermediate Mass Boson. There was no fanfare, no celebration. Just a heavy silence, thick with the awareness of what they were about to do. They were proposing the first fundamental addition to the standard model of particle physics in half a century. They were throwing a gilded wrench into the smooth, elegant machinery of modern science. With a final unanimous nod, Dr. Thorne moved her cursor over the Submit button on the online physics preprint server. It was a simple, anticlimactic click. But it was a click that would echo through every university and research institute on the planet. Their paper went live at 4 Neuro AM Geneva time. It was a spark thrown into the vast interconnected network of global physics. Within minutes, automated alerts were pinging on the phones of researchers in Tokyo and California. By sunrise in Europe, it was spreading like wildfire. Emails flew across continents. Video calls were hastily arranged. In laboratories and university corridors, the quiet hum of the day's work was replaced by frantic, excited and deeply skeptical conversations. The Ethelgard group had not just published a paper, they had issued a challenge to the entire scientific community. They had drawn a new map of reality and dared their colleagues to prove it wrong. The years of quiet frustration were over. The era of doubt had ended. A new uncertain and exhilarating hunt had just begun. The question was no longer what these strange signals from space meant. The question now was sharp, terrifying and thrilling as the exposon real. And so the signal that had whispered its secret from the edge of oblivion now roared across the globe. It did not arrive like a thunderclap, but like an insidious, irresistible tide seeping into the servers and inboxes of every major physics department on the planet. The preprint paper, A Declaration of Cosmic Heresy, became an overnight obsession. In Munich, coffee went cold as theorists frantically scrawled equations on glass walls, their reflections ghosts in a flurry of new symbols and imagined interactions. In Tokyo, supercomputer time was requisitioned with an urgency usually reserved for tsunami warnings, as programmers worked to build simulations of this impossible particle. The initial shockwave of the discovery, which we felt so viscerally with the Discovery team, had now fractured into a million points of intense focused and deeply skeptical light. For science is not a gentle march toward truth. It is a brutal, glorious battlefield of ideas, and a claim this extraordinary required an extraordinary defence. The unspoken question echoed in every hushed corridor and every frantic video call. Was this the dawn of a new physics, or the grandest mistake in a generation? The world's most formidable minds were now mobilising not to celebrate, but to attack. They came for the data first, as they always do. This is the brutal crucible of modern science, a forensic process of peer review that is less a review and more an interrogation. Independent teams from rival universities and competing national laboratories descended upon the public data archives like digital vultures. They were not looking for confirmation. They were hunting for the fatal flaw, the subtle oversight, the ghost in the machine that would explain everything away and restore the comfortable order of the universe. At CERN, a specialised group known for its ruthless analysis of particle collision data repurposed its formidable algorithms, turning them away from the LHC's wreckage and pointing them toward the cosmos. Their approach was purely adversarial. Every line of code the original team had written was meticulously unspooled and re-examined. Was there a rounding error buried deep in a statistical library, a miscalibration in the satellite's gamma-ray detector that was only triggered by particles arriving from a specific unusual angle? Could cosmic dust charged in a previously unmodelled way mimic the signature? They built a shadow model, a digital twin of the entire experiment, but programmed it with a single directive: find another way. Find any path, no matter how convoluted, that leads to this anomalous energy spike without invoking a new particle. For weeks their servers churned, testing thousands of permutations, pitting every known particle against every known environmental variable. They were trying to prove a negative to demonstrate that the phantom was in fact just a shadow. Simultaneously at Fermilab outside Chicago, a different kind of hunt was underway. Here they did not trust the reanalysis of old data alone. The ghosts of past discoveries, later revealed to be statistical flukes, haunt these halls and serve as a constant humbling reminder. You must see it again with your own eyes, with your own machine. A team there pivoted their work on a dark matter detection experiment, a vast shielded vat of liquid xenon buried a mile underground. Their detector was not designed to see particles from distant quasars, but to catch the whisper-faint signature of a dark matter particle, a WIMP drifting through the Earth and striking a xenon nucleus. But the theory behind this new cosmic particle suggested a tantalizing possibility. If it truly existed, it might decay into other more familiar particles, like exotic neutrinos that could be seen by their terrestrial experiment. The signal would be different, an echo rather than a direct observation, but its presence would provide the crucial independent corroboration the world was waiting for. So they began to sift through their own years of data, not for the single billiard ball-like collision they had been searching for, but for a far more subtle pattern. A slight inexplicable excess of low-energy events, a faint rhythmic pulse in the data that could correspond to the slow decay of this new entity as it passed through the planet. It was akin to listening for a single cricket's chirp in the heart of a hurricane, a search for a signal so faint it bordered on the philosophical. Yet they searched, because the prize, if real, was worth any effort. The careers of these scientists, their entire understanding of their field, were balanced on a knife's edge, waiting for a blip on a screen, in a cavern of perpetual darkness, and as the experimentalists toiled in their digital forges and subterranean cathedrals, the theorists waged a war on a different plane of reality. They proposed alternative explanations that were in their own way as beautiful and strange as the new particle itself. Perhaps one prominent group from Caltech argued it wasn't a particle at all. Perhaps it was a wrinkle in the fabric of space-time itself. They postulated that under the extreme gravitational and magnetic conditions near a supermassive black hole, quantum field theory might permit a vacuum excitation, a momentary localized bubbling of reality that borrows energy from the vacuum, shines brilliantly for an instant, and then collapses back into nothingness. This fleeting mirage of energy would look to our detectors exactly like a particle decay. It was a breathtakingly elegant idea, one that required no new pieces on the cosmic chessboard, only a deeper, more profound understanding of the rules of the game. It preserved the sanctity of the standard model, but at a cost it suggested that the vacuum, the very definition of nothing, was a far more volatile and unpredictable place than we had ever dared to imagine. It hinted that the universe could conjure ghosts from its own emptiness. Another camp working from Princeton offered a darker, more troubling possibility. What if the anomaly was real, but its origin was far more mundane? They focused on the astrophysics of the source itself. The particle's signal came from the accretion disk of a quasar, one of the most violent and complex environments in the known universe. Their models, far more intricate than any previously attempted, suggested a new type of plasma oscillation, a collective resonance of electrons and positrons caught in a tangled knot of magnetic fields and superheated to trillions of degrees. Under just the right, exquisitely rare conditions, this plasma could create a pseudo-particle, a coherent wave of energy that would travel across billions of light years and strike our detector with the precise energy signature that had been observed. This explanation was in many ways the most terrifying for the Discovery team. It didn't challenge the foundations of physics, but it implied that our understanding of astrophysics was profoundly incomplete. It meant that the universe was simply more clever than we were capable of creating convincing illusions that could lead us on a wild goose chase for a generation. It was the ultimate cosmic misdirection. The original signal would be real, but its meaning would be hollow. The spectre of this possibility cast a long shadow, a reminder that nature is under no obligation to be simple, or to provide us with unambiguous answers. Yet amid all the skepticism and the search for conventional explanations, a powerful and exhilarating new idea was taking root. What if the particle was real? What if all the counter-arguments failed, and the signal was confirmed again and again? Then you are forced to ask a question that changes everything. What does this particle do? Every known particle is a cog in a grand machine. It plays a role. The photon carries the electromagnetic force, binding atoms together and letting you see the world. The gluon carries the strong nuclear force, gluing atomic nuclei together and preventing the universe from dissolving into a quark soup. The W and Z bosons carry the weak force governing radioactive decay and helping stars to shine. The graviton, though still hypothetical, is believed to carry gravity anchoring you to the Earth and choreographing the dance of galaxies. These are the four known forces, the four fundamental pillars upon which all of reality rests. But they are not enough. They cannot explain the great mysteries that haunt the edges of our cosmological maps. They cannot explain the phantom gravity that sculpts galaxies, which we call dark matter. They cannot explain the accelerating expansion of the universe, which we call dark energy. The Standard Model, for all its triumphant success, is a masterpiece with missing chapters. It describes with breathtaking precision a mere 5% of the cosmos. The rest is silence. This is where the new particle ignites a revolution. Theorists began to model its properties not as a lone entity, but as a messenger, a harbinger, the mediator of a fifth fundamental force of nature. Imagine for a moment that the universe we know, the universe of light and matter of stars and planets and people, is just one side of a vast cosmic tapestry. On the other side, unseen and unfelt, is the dark sector, a shadow universe of dark matter and dark energy governed by its own rules, its own particles. For decades we have assumed these two realms were almost completely separate, touching only through the gentle, indiscriminate pull of gravity. But what if that's not the whole story? What if there is a back door, a secret channel of communication? This new particle, this quintessence boson, as some began to call it, could be the key to that door. It could be the agent of a new force that feels both normal matter and dark matter, a force that acts as a bridge between the luminous world and the hidden one. Suddenly, dark matter is no longer just a passive gravitational ghost. It becomes an active participant in the universe's physics, capable of interacting, of clustering, of decaying through this new fifth force. The anomalous rotation of galaxies might not just be due to the mass of dark matter, but also due to it pushing and pulling on itself through this new interaction. The empty voids in the cosmic web might be carved out not just by gravity, but by a repulsive aspect of this fifth force, a kind of cosmic anti-gravity acting only within the dark sector. The discovery of a single particle would not just add a new column to our charts, it would unveil an entirely new dynamic and complex shadow reality that has been running in parallel to our own for 13 billion years. The implications spiral outward, becoming more and more profound. We must consider the nature of this proposed force. All the evidence points to it being incredibly weak and extremely short range. If it was strong or long range like electromagnetism, we would have seen its effects everywhere. It would have altered the orbits of planets, the fusion rates in stars, the very chemistry of life. Its subtlety is the very reason it has remained hidden for so long. It operates in the margins, a tiny correction to the grand equations of reality. Perhaps it only becomes significant under the most extreme conditions, like in the crucible of the Big Bang, or in the hyperdense cores of neutron stars, or in the churning chaos around a supermassive black hole exactly where the signal was born. This fifth force might be the universe's hidden regulator, a fine-tuning knob that only operates at the extreme, setting the stage for the cosmos we see today, and then retreating into the shadows. It might have governed how dark matter decoupled from normal matter in the first seconds of creation, shaping the very seeds from which galaxies would eventually grow. We might be living in a universe whose large-scale structure was fundamentally sculpted by a force we have never even known existed, and then you arrive at the final, most unsettling frontier of this idea. The very concept of a physical constant is something we hold dear. The speed of light, c. The gravitational constant, g. The fine structure constant alpha, which governs the strength of electromagnetism. We assume these are immutable universal values woven into the very fabric of space-time, the same yesterday, today, and in a billion years, the same here as in the Andromeda Galaxy. But what if they are not? What if some of these constants are actually dynamic fields, their values dependent on local conditions? If a fifth force exists, and if its carrier particle interacts with both dark matter and our own fields, it opens a terrifying and exhilarating possibility. The strength of this fifth force might depend on the local density of dark matter. And if this force can subtly influence electromagnetism, even by a trillionth of a percent, then the fine structure constant might not be a constant at all. It might flicker. In a galaxy dense with dark matter, the laws of chemistry could be infinitesimally different than in a galaxy with less. The very light emitted by an atom there could be shifted to a slightly different colour. The stability of matter itself could be subject to the whims of the unseen. We look out across the cosmos and assume we are seeing a single unified set of rules in action. But we could be looking at a cosmic patchwork, a universe, where the fundamental constants are not baked in, but are instead a local environmental variable like the weather. This doesn't just challenge the standard model, it challenges the bedrock philosophy of physics since Newton, the assumption that the laws we uncover in our laboratories apply everywhere and for all time. The signal from that one distant quasar was no longer just a curious anomaly. It had become a profound existential question, asking us if we truly understand the nature of reality, or if we have merely been observing a single quiet parish in a vast and varied cosmic country. All these theories, all these frantic searches and deep-seated doubts were now converging on a single point in time. Deep beneath the Gran Sasso mountain in Italy, another team of scientists had been running a dark matter experiment different from the one at Fermilab, using a different methodology, a different target material and a different analysis. For months they had maintained a strict disciplined silence, refusing to comment on the initial discovery, simply continuing their work. But now the rumours were beginning to fly. They had finished their analysis. They had seen something. A date was set for an announcement. The entire world of physics held its breath, poised between two realities. In one, the universe would snap back to the familiar, the anomaly would be explained away, and the standard model would reign supreme once more. In the other, a single data plot presented in a quiet conference room in Europe would confirm that everything we thought we knew about the cosmos was wrong, and that the search for understanding had to begin all over again in a universe suddenly far stranger and more magnificent than we had ever dreamed. The weight of 5 centuries of physics was about to rest on the outcome of a single experiment. For months, the silence was the loudest sound in physics. The tantalizing whispers from deep space, those anomalous flickers in the cosmic microwave background, had found no immediate echo in the cathedrals of science on Earth. The search, as we had seen, had fractured into a dozen disparate efforts, each pursuing a ghost down a different darkened corridor. Skepticism, that essential and formidable guardian of scientific integrity, had begun to reassert its grip. The initial flurry of excitement was settling into a long, uncertain winter of painstaking work, where every null result felt like another stone wall erected against the path of discovery. The proposed particle, this phantom messenger of a new force, remained just that, a phantom, a beautiful and compelling theory haunting the margins of our understanding. It was a time of immense pressure where the greatest risk was not being wrong, but of being forgotten, of the anomaly being dismissed as a statistical fluke, a ghost in the machine. Then, from a cavern of magnets and supercooled sensors buried deep beneath the Swiss-French border, a new sound began to emerge. It was not a shout, not at first. It was a pulse, a faint but unnervingly regular beat, where there should have been only the random static of quantum noise. This was the Helios experiment, a machine designed not with the brute force of the Large Hadron Collider, but with the subtle precision of a watchmaker. Its sole purpose was to recreate the specific peculiar energy conditions observed in those dying stars we had studied, the very places where our phantom particle was first suspected to be born. It was a targeted search, an arrow aimed at a very specific spot in the vast darkness. For 2 years, its heart of purified silicon crystals had been bombarded with a focused beam of positrons, searching for a single forbidden decay, a pathway that simply cannot exist within the known laws of physics. And for 2 years, it had found nothing. But then, in the early hours of a Tuesday in October, the algorithm flagged an event. A positron had struck a silicon nucleus, and instead of recoiling in the expected way, had vanished. In its place, for a fleeting picosecond, a surge of energy had blossomed and then decayed not into the familiar photons of light, but into an electron and its antimatter twin. This was the exact signature, the specific fingerprint, the theoretical post-it note left by our ghostly quarry. It was a single event, statistically insignificant, and was nearly dismissed. But a week later, it happened again, and again the following month. Slowly, painstakingly, the team shielded their work from the world, battling their own confirmation bias, tearing their own methods apart, trying desperately to prove themselves wrong. They recalibrated their sensors, redesigned their magnetic containment fields, and recalculated the background noise 1,000 times over. The signal refused to disappear. It was real. Buried within the data like a fossil in ancient stone was the unmistakable bump in the energy spectrum at 17 mega-electron volts. It was the echo, the confirmation from Earth of the very same mass we had inferred from the starlight of a distant galaxy. The team, led by a physicist who had staked her entire career on this long-shot experiment, could finally admit what they were seeing. They had captured the phantom. The particle was no longer a cosmic maybe. It was a terrestrial fact, a fleeting but repeatable guest in their machine. The news, when it was finally released, did not explode upon the scientific community. It landed like a profound and deafening thunderclap, a seismic event that sent shock waves through every university and laboratory on the planet. The first key had been forged, and it had turned a lock no one was even sure existed. But a single experiment, no matter how precise, can be an anomaly. A systematic error, some unknown variable, could still be at play. The true revolution in science requires not a single voice, but a chorus. The second voice in that chorus would come not from a particle accelerator, but from the coldest, loneliest depths of the cosmos. Thousands of light years away in the constellation of Vela lies a city of the dead. It is a graveyard of white dwarf stars, the smouldering compressed embers of suns that exhausted their fuel billions of years ago. These stellar remnants should cool at a predictable rate, radiating their residual heat into the void like dying campfires, their thermodynamics governed by well-understood physics. For decades we have used them as cosmic clocks, their steady cooling a reliable metronome against which we can measure the age of the universe. Yet for just as long, a nagging discrepancy has puzzled astrophysicists. A certain class of these white dwarfs, the most ancient and massive among them, appeared to be cooling down far too quickly. It was as if they possessed a secret, an extra exhaust vent through which they could shed their thermal energy, defying the equations that described their cousins perfectly. Dozens of theories had been proposed, exotic crystal structures in their cores, strange magnetic field interactions, but none fit the data. The problem was shelved, filed away under unexplained phenomena. But in the wake of the Helios discovery, a young team of theorists in California decided to ask a wild question. What if this secret exhaust vent wasn't a property of the star itself? What if something was actively stealing its heat? They took the precise mass and interaction strength of the new 17 MeV particle, detected in Switzerland, and plugged it into their stellar evolution models. They were creating a simulation of virtual white dwarf inside a supercomputer, and for the first time they gave it the ability to create this new particle in its intensely hot, dense core. The simulation ran for 3 days. What emerged was nothing short of miraculous. The model, now imbued with this new law of nature, predicted a cooling rate that matched the observed data from the Vela graveyard, with breathtaking tenth of a decimal point precision. The new particle, this so-called X17 boson, acted as a cosmic refrigerant. It could be spontaneously created from the thermal chaos of the star's core, and because it interacted so weakly with ordinary matter, it could stream out into space unimpeded, carrying away energy far more efficiently than sluggish photons or neutrinos ever could. It was the missing piece. The key forged in the heart of a terrestrial machine fit a cosmic lock half a galaxy away. This was the moment the paradigm shifted. This was the convergence. Two utterly independent lines of evidence, one from the meticulously controlled environment of a particle accelerator and the other from the wild, untamed laboratory of the cosmos, were pointing to the exact same conclusion. It was as if a biologist studying a new species of deep-sea fish and an astronomer studying the atmospheric composition of Jupiter both discovered the same unknown amino acid. The sheer improbability of such a coincidence was staggering. It could no longer be a fluke. The world of physics began to move, the great ponderous creature slowly turning its head to look in this new direction. Emergency colloquiums were organised preprint servers, crashed under the traffic, and old rivalries were forgotten in the face of a shared electrifying mystery. This was no longer just about a new particle. A new particle implies a new force, the standard model. Our grand theory of nearly everything is a perfectly balanced equation of 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Each force has a carrier particle, a messenger, that communicates its influence. The photon carries electromagnetism. Gluons carry the strong force. Now it seemed a 5th column had been discovered. A new force of nature, one that had been operating silently in the background of the universe since the Big Bang had just been unmasked. And the properties of this force were unlike anything we had ever imagined. It appeared to be strangely shy, interacting very weakly with the protons and neutrons that make up our world, which is why it had remained hidden for so long. But its behaviour hinted at something far more profound. Early models frantically coded in the weeks following the convergence suggested that this 5th force might not care much for our kind of matter at all. Instead, it seemed to have a deep and powerful affinity for the one thing we cannot see: dark matter. You see, the great embarrassment of modern cosmology is that the 95% of the universe we call dark matter and dark energy remains a complete enigma. We can map the gravitational shadow of dark matter, we can see how it sculpts galaxies and bends starlight, but we cannot touch it. It flows through our bodies, our planet, and our detectors as if we are not even here. It has, for all intents and purposes, been a ghost haunting the cosmos. But what if this new force was the missing link? What if it was the bridge, the cosmic Rosetta Stone that could finally allow us to communicate with the dark side of the universe? Theorists began to call it the dark force, a fundamental interaction primarily between dark matter particles. Our world of protons and electrons would only feel its influence through a tiny, almost imperceptible leakage, a quantum mechanical portal that allowed the X17 boson to occasionally pop into our reality before decaying away. This theory explained everything. It explained why the particle was so hard to detect on Earth. It explained its subtle influence on stellar evolution. And most excitingly, it offered a potential explanation for the very structure of the universe itself. Massive computer simulations of cosmic evolution have always struggled to perfectly replicate the universe we see today. They get the big picture right, the great filaments of galaxies and the vast voids between them, but they fail on the smaller, more intricate scales. They predict that large galaxies like our own Milky Way should be surrounded by thousands of smaller satellite dwarf galaxies, yet we observe only a few dozen. This missing satellites problem has been a persistent thorn in the side of cosmology. But when you add a 5th force to these simulations, a force that allows dark matter particles to interact with and push against each other slightly, the picture changes dramatically. The force prevents the dark matter from clumping together too tightly in the centres of galaxies. It smooths out the cores, starving the formation of those thousands of predicted dwarf galaxies. The simulation for the first time begins to look exactly like the sky we see through our telescopes. This was the tipping point. The convergence of evidence from particle physics, stellar astrophysics, and galactic cosmology was a trifecta of such immense power that the foundation of the field began to tremble. The fifth force was no longer a fringe hypothesis relegated to late-night conference discussions. It was now the leading contender, the primary candidate for the next great leap in our understanding of reality. It had graduated from a question mark to a bold italicized statement. We were looking at the dawn of a new physics, a more complete, more complex, and infinitely more interesting description of the universe. The old maps, the beautifully drawn charts of the standard model were not wrong, but they were suddenly shockingly incomplete. An entire continent, a whole new realm of interaction had been sitting just over the horizon, and we had finally, after a century of looking, caught our first glimpse of its shoreline. But this grand emerging picture is not without its own shadows, its own new puzzles. The X-17 particle seems to behave slightly differently in different environments. Its interaction strength, the very volume of its voice, appears to change depending on the energy of its surroundings, a chameleon-like quality not predicted by our initial simple models. Some data suggests it may even have heavier undiscovered siblings, a whole family of dark messengers. We have found the first letter of a new alphabet, but we do not yet know the words it can spell or the stories it can tell. The consensus is that we have found something real, something transformative. But the final definitive proof, the kind of 5 sigma certainty that allows for Nobel Prizes and rewriting of textbooks, is still just out of reach. We have followed the evidence to the edge of a vast new ocean of discovery. The climax of our search has led not to an ending, but to a profound, exhilarating new beginning. And now the challenge is to build a ship capable of sailing those unknown waters. And so the silence that follows such a revelation is profound. It is the quiet intake of breath before the world changes forever. For decades we walked the halls of a magnificent cathedral, the standard model of particle physics, believing we knew its every arch, its every stained glass window, depicting the forces of creation. We had grown comfortable within its hallowed walls, so comfortable that we almost forgot we built it ourselves. It was our grandest monument to the power of reason, a testament to our ability to decipher the very grammar of reality. But the data we have just witnessed, those whispers from the void, are not a new hymn to be sung in the same old choir. They are the sound of a wrecking ball meeting stone. They are the undeniable proof that our grand cathedral, for all its beauty and predictive power, is not the whole of existence. It is merely a chapel attached to a far vaster, stranger, and more mysterious structure we are only now beginning to glimpse. To say this discovery necessitates a revision of the standard model is a profound understatement, akin to saying the discovery of America merely required a revision of local European maps. It does not simply add a new column to a familiar table, or a new character to a well-understood story. It forces us to question the foundation upon which the entire edifice rests. Every particle we thought was fundamental must now be re-examined. Every interaction we believed we had catalogued is cast in a new uncertain light. The delicate, almost miraculous balance of constants that allows for our existence, the precise strength of electromagnetism that holds your body together, the nuclear forces that power our sun, all of it was calculated without this new player on the board. A fifth force is not an additive. It is a transformative agent. It suggests a new symmetry in the universe, a new organizing principle that has been operating in the shadows since the first moments after the Big Bang. Physicists around the world are now faced with a task both thrilling and terrifying: to tear down a temple they revered, salvaging what is true while making space for a greater, more complex reality. They are not just adding a room, they are redesigning the cosmos, and in that redesign we find our first tantalizing clue to one of the most persistent phantoms in the cosmic story, dark matter. For nearly a century we have known the universe is haunted. We have watched galaxies spin with a speed that should tear them apart, their visible stars and gas held in check by an immense, unseen gravitational grip. We have mapped the light from the early universe as it bends and warps around invisible scaffolds of matter, a ghostly architecture shaping the cosmos on the grandest of scales. This is dark matter, an invisible ocean through which our own island of normal matter sails. It outweighs us 5-1, yet it has remained stubbornly, infuriatingly aloof. It does not shine, it does not reflect, it does not absorb light. It feels gravity but seems to ignore every other force we know. It passes through you, through the earth, through the heart of the sun, as if none of it were there at all. We have been searching for a bridge or portal, some way to interact with this dark sector. And now, with this discovery, we must ask the most exhilarating question of all. What if this new particle, this carrier of a fifth force, is that bridge? What if this force is the language that dark matter speaks? Imagine a universe filled with two distinct forms of existence living side by side but mutually invisible, like two different radio stations broadcasting on different frequencies. For eons, we have been tuned to only one channel, the channel of electromagnetism, the strong and weak nuclear forces. This discovery is like building a new kind of radio receiver, and for the very first time hearing the static of that other hidden station. Perhaps this fifth force allows dark matter to interact however weakly with our world. Perhaps dark matter particles can feel this force, can exchange these newly discovered bosons, and in doing so can leave subtle, fleeting fingerprints on our experiments. Suddenly the global hunt for dark matter is transformed. Detectors buried deep underground, designed to catch a rare billiard ball-like collision from a dark matter particle, may need to be redesigned. They now have to look for the signature of a new force, a new kind of energy. We are no longer searching for a silent ghost in the dark. We are searching for the whisper of a new conversation, a fundamental dialogue between the visible and the invisible halves of our universe. This is our cosmic Rosetta Stone, the key that could finally allow us to translate the secrets of the dark, silent majority of creation. It promises to reveal not just what dark matter is, but how it shaped the galaxies, how it forged the cosmic web, and how it set the stage for our own unlikely emergence. The implications, however, do not stop in the dark. They stretch to the furthest horizons of space and time, to the very fabric of the expanding cosmos and the mystery of dark energy. If dark matter is the universe's invisible skeleton, dark energy is its runaway heart pumping space-time itself outwards at an ever-accelerating rate. We see its effects everywhere. Distant galaxies are not just receding from us, they are fleeing faster and faster, propelled by an unknown repulsive force woven into the vacuum of space itself. This is without question the deepest enigma in all of physics. It violates our intuition about gravity, which should be pulling things together, slowing the expansion down, not speeding it up. The Standard Model has absolutely nothing to say about it. It is a profound and humbling failure of our best theory of reality. But could a fifth force offer a new path forward? This is more speculative, a leap into the intellectual frontier, but it is a leap physicists are now willing to take. Perhaps this new force we've detected is not always confined to the subatomic realm. Perhaps over vast cosmic distances it doesn't just mediate interactions between particles, but also interacts with the geometry of space-time. Could dark energy, this mysterious pressure pushing the universe apart, be a macroscopic manifestation of this fifth force? Could the energy of the vacuum, which we now know is seething with quantum fields, be channeled by this new interaction into a relentless cosmic acceleration? This would be the ultimate unification, connecting the bizarre behavior of decaying particles in a laboratory with the ultimate fate of the entire universe. It would mean that the same fundamental rule that governs a single exotic atom is also writing the final chapter of cosmic history, determining whether the cosmos ends in a freezer rip or something else entirely. We have always looked for a theory of everything, a single equation that could unite the very large with the very small. Perhaps we have just stumbled upon a crucial verse in that ultimate cosmic poem, a verse that links the quantum foam to the galactic supercluster, the fleeting moment of particle decay to the endless eons of cosmic expansion. This is the holy grail of modern physics, a complete theory of nature. For a century our quest has been stalled by one colossal obstacle: gravity. Einstein's general relativity, our theory of the very large, describes gravity as the elegant curvature of space-time, a smooth, beautiful ballet of planets and stars. Quantum mechanics, our theory of the very small, describes a world of frenetic, pixelated uncertainty, a jittery dance of particles and fields. The two theories are magnificent triumphs in their own realms, but where they meet in the heart of a black hole or the inferno of the Big Bang, they break down. They give us nonsense. They speak different languages, and the universe becomes an indecipherable roar. A fifth force could be the translator we have desperately needed. Most attempts at a quantum theory of gravity, like string theory, predict the existence of extra forces and exotic particles as a matter of course. They are not an inconvenience, they are a core feature. For decades, these predictions were purely mathematical abstractions existing only on blackboards and in the minds of theorists. Now, for the first time, we may have a genuine physical thread to pull on. This new particle might be the first glimpse of a much larger, more complex quantum structure that underpins reality. It might be our first direct evidence of hidden dimensions of space, or the first sign of a grander symmetry that unifies gravity with all the other forces of nature. If this is true, then we are on the verge of the greatest revolution in physics since Einstein. We would finally have a theory capable of describing the universe at the moment of its birth, a theory that could answer the ultimate question: where did all of this come from? The discovery of a fifth force doesn't just challenge the standard model, it provides the first real tangible stepping stone across the gaping chasm that separates our two best descriptions of reality. It's a beacon in the dark pointing the way toward a unified theory of everything. And as we redraw the fundamental laws of physics, we must also begin to rewrite the textbooks for nearly every other science. Consider the lives of stars. Our models of stellar evolution of how stars fuse elements in their cores, how they live and how they die, are all built upon the foreknown forces. But if there is a fifth force at play, even a very weak one, its effects inside the ultra-dense, ultra-hot crucible of a stellar core could be cumulative and profound. It could subtly alter the rate of nuclear fusion, changing a star's brightness, its lifespan, its temperature. It could affect the way a massive star collapses into a supernova, potentially solving long-standing puzzles about the mechanics of these cosmic explosions. It could even change the nature of the exotic objects left behind, like neutron stars and black holes. These are no longer just masses of crushed matter governed by gravity. They are now potential laboratories for fifth force physics, places where its effects might be amplified to an observable degree. The same is true for the formation of galaxies. Our simulations of how vast clouds of gas and dark matter collapsed to form the spiral cities of stars we see today will have to be rerun. A new force, especially one that couples the visible and dark sectors, would be a powerful new ingredient in this cosmic recipe. It could explain anomalies in galactic structures that have puzzled astronomers for years. It could change how quickly galaxies form, how they cluster together, and how the supermassive black holes at their centres grow to such enormous sizes. From the smallest star to the largest supercluster, every object in the astronomical zoo must now be seen through a new lens. We have to look at the entire universe again as if for the first time, and ask where else have the fingerprints of this force been hiding, mistaken for something else, or dismissed as mere noise in our data. This revolution extends even to one of the most personal and profound human questions: are we alone? Our search for extraterrestrial intelligence has been predicated on a simple assumption that any technologically advanced life would like us discover the laws of electromagnetism and use it to communicate. We've been scanning the heavens for radio waves, for laser pulses, for the familiar signs of a technology built on the same physics as our own. But a fifth force opens up a startling and humbling possibility. What if there is a form of life, perhaps even a technological civilization, that evolved in a way that is deeply connected to this other hidden physics? What if it communicates not with light, but with focused beams of these new particles? What if its technology is based not on electronics, but on manipulating this new force field? Such a civilization could be all around us, shouting at the top of its lungs, and we would have remained utterly, completely deaf and blind. Our radio telescopes would hear nothing but the hiss of empty space. Our optical telescopes would see nothing but silent stars. We have been searching for our own reflection in the cosmic mirror, but the universe may be vastly more creative than that. This discovery doesn't just give us a new place to look for life, it gives us a new way to listen. a new sense with which to perceive the cosmos. It compels us to build new kinds of telescopes, new detectors designed to intercept messages we couldn't even have imagined a few years ago. It forces us to confront the possibility that the universe could be teeming with a kind of life and intelligence so fundamentally different from our own that it has remained hidden in plain sight. The great silence that seems to permeate the cosmos might not be an absence of voices, but simply a failure of our hearing. Ultimately, this journey into the heart of matter and the edge of the cosmos brings us back to ourselves, to the human spirit of inquiry that set us on this path in the first place. Every great scientific discovery is at its core a story of humility. It is a moment when we are forced to shed our certainty, to admit the limits of our understanding, and to embrace the unknown. For centuries we thought the Earth was the centre of the universe. We were wrong. We thought our galaxy was the only one. We were wrong. We thought the matter we could see was all that existed. We were wrong again. And now the four forces we believed were the complete set of rules for the cosmic game have been shown to be an incomplete list. Each of these revelations did not diminish us. Instead, they expanded our sense of the possible and deepened our appreciation for the magnificent complexity of the universe we inhabit. This discovery is the latest and perhaps the greatest chapter in that ongoing story. It reminds us that reality is always richer and more nuanced than our current theories allow. It proves that even after centuries of observation and exploration, the cosmos retains its infinite capacity to surprise us, to enchant us, and to challenge our most cherished assumptions. We are not at the end of discovery. We are, it seems, at a new beginning. The path forward is now clear, though it will not be easy. A new generation of particle accelerators, more powerful than any built before, will be designed specifically to produce and study this new force. Space-based observatories and ground-based telescopes will be retasked to hunt for its astrophysical signatures. An army of theorists will work to build a new standard model to find a place for this discovery within a grander, more elegant mathematical framework. There will be wrong turns, dead ends, and fierce debates, but the chase is on. We are explorers who have just found that the map we were using showed only a tiny fraction of the world. Beyond the edges of our knowledge, a new ocean has appeared, and we are now building the ships to sail it. What we will find in those uncharted waters is anyone's guess. New particles, hidden dimensions, answers to the nature of reality itself. We do not know, and that is the most beautiful thing of all. The quest for knowledge is not about finding final absolute answers. It is about the relentless, joyful, and deeply human process of asking the next question. It is about looking out into the vast, silent darkness of the universe, not with fear, but with a boundless and unyielding curiosity, knowing that for every mystery, we solve an even more profound and wonderful one is waiting to be unveiled. The journey does not end. It has just begun.